In this section, we'll go through several steps that you might take if you're trying to look at starting a new generator. So those might involve running contingency analysis and comparing contingency analysis runs on a base case versus one with the generator interconnected. Might involve doing some PTDF sensitivity analysis and also visualizing things like that on a one-line diagram. It might involve PV and QV and several other aspects as well. So we'll kind of go through each of those. So in many ways, this is kind of a review section because we're going to be using tools for the most part that we've already looked at in other parts of the training, with the exception of doing the comparison of two sets of contingency results, because that'll be something we hadn't covered. So the case that we'll use is called the Active SG2000. It's a 2000 bus case with a footprint over the state of Texas. And so I'll switch over to simulator and then open that one. It should be in the top level training cases directory. And one of the things we'll want to do initially is go into the simulator options, and then on the common options tab right here, check the box that says prevent controller oscillations. And then I can open my message log and just make sure that the case solves and that we've got a good base case. All right, so what we'll do with the new generator is we're going to assume it's interconnected at bus 1089, which is an existing bus in the case at the La Mesa substation, and we'll give the generator a new bus that'll be interconnected at bus number 1, and we'll model that at 34.5 kV, put it in its own area, number 10, which we'll call La Mesa, in zone 1 and part of substation 54. Those are all properties of the bus. We'll insert a transformer that connects the new bus 1 to the existing bus 1089 with these impedance parameters right here. And we'll just leave the limits at 0 because we're not really going to study whether or not we're violating a limit on a step-up transformer. We're not concerned with that. We're going to just assume that that's going to be sized properly to handle the output of the generator. Then we'll add the generator to this bus and give it these parameters of 200 megawatts maximum, regulating the high voltage bus 1089 to 1.0 per unit volt with this range of reactive power outputs. We can look here in the bus view one line at bus 1089. This is where it'll be added. And if we wanted to see kind of where this is on the one line diagram, we can seek that out as well. Go to, we don't have buses. This is a substation diagram. Substation 54 is located right here. And if we zoom back on that, it gives some perspective of where it is in the system. So it's kind of out on the edge. So we'll be interested in finding out through this process whether we have enough transmission capacity to deliver power from that point to other points in the system, and what that does to voltages and what it does to the contingency overloads. We can just do all this by loading it from this auxiliary file here to aux 2020 generator interconnect. And if I come back over here to simulator and click the load auxiliary file, I can look inside the S08 folder and it's this one right here, and I'll just open it in a text editor to show you what we're doing if we load this file. It'll switch to edit mode with that script right here. It'll add a bus, number 1, called La Mesa Wind with 34.5 kV nominal voltage, so it's kind of like a collector bus for a wind farm. It could be. We'll add a generator at that bus with these parameters right here, which are described also in the slide, and then provide a transformer that connects that new bus to the existing La Mesa bus 1089. We'll provide a new area that we'll call La Mesa. By providing a new area where this bus is the only bus that belongs to it, it allows us just to use the area objects to do transfers with ATC and with PTDF quantities if we wish to do it that way. We'll also use injection groups in this example, which we'll need to do for PV analysis, and also it gives us a lot of flexibility for the other types of analysis. But areas are often an easy way to set up transactions if we want to sync the power from that new generator to one of the other areas in the system. We can even do multiple analyses where we're choosing different buyers for that transaction. So it just gives you a lot of flexibility in how to set up your case if you do it this way. We could also drop it into an existing area, but then we would be having to adjust exports from that existing area and or backing down generation in that existing area in order to accommodate the new injection. So this just gives us more flexibility. Here's a transaction that we're going to initially add to sync the generation from the new area to area 7, which has a name Coast in the case. And initially that won't be enabled so that we can toggle it on if we need to. So that's what that does. What I'll do now is just load it. And then I should be able to verify that there's no issues. If I look at my message log, I can see that the bus is added, the generator, the branch, the area, and the study transactions there. Now if I go back to my bus view, I probably need to refresh this a little bit. I'll just switch to a neighboring bus and then go back to La Mesa. This is what was added right here, this little piece. So here's the existing bus that was in there before. It's at a nominal kV of 115. Now we have a new generator, a new bus, and a step-up transformer from the collector voltage to transmission voltage. And initially everything's disconnected. So if I solve the power flow right now, I shouldn't get any movement of the system state from what it was before. But if I put that generator in and I sync the power somewhere, then of course adjustments would be made. All right, so next what we're going to do is we'll create some injection groups which we can use as sources and sinks for the ATC and PV analysis that we'll do later. And usually when you're doing PV analysis, at least, you're studying the ramping of the generator and also ramping of load somewhere else up, although you can certainly do whatever you want with PV analysis, as we discussed in the prior section. But we'll just load an auxiliary file that'll do this and just take a look at what it did. There's an injection group that'll be called La Mesa, which will contain only the new generator, and then another group called Coast Load, which will contain all the loads in Area 7. We'll just go to load that right here from loading auxiliary file, and we'll pick the one AUX 2030 injection groups. And we'll just say yes to all for any confirmation dialog that pops up. Now if I go to my Model Explorer and I look under aggregations at injection groups, I can see I have these two new groups, one called Coast Load, which has 242 loads in it, and the participation factors are all based on the size of the load. So when we ramp a transaction, the larger loads, the loads will move up in proportion to their size. So they'll all move up the same percentage. And there's another one called La Mesa. It's grayed out right here because its only participation point is offline, but that'll change later as we get into the analysis. If we were manually adding them, we could make use of area zone filters to look only at area 7 and then select all of the loads in the list and then add them and initialize the participation factor to be proportional to the size. All right, so we're also going to need to make some adjustments to our AGC settings so that we can do these transactions. And this is something you might encounter in cases that you're working with. We just have one island in this small case. So we have one island slack bus, and it's presently in, I believe, area 7, which is why we want to move it, because we're going to make transactions that go to area 7. And so we don't want the system slack generation responding to small changes in load or losses within that area. We want that to be somewhere else in an area that we're not studying. So if I come over here to my Model Explorer and I look at islands, I can see I have just one, and it's in area coast. So we want to move that, and we'll just move it to another bus with a large generator, bus number 5262. If I take a look at what that looks like here in the bus view one line, it's got a large nuclear facility, and it's in a different area, one that we're not going to sync power directly to. We'll do that. We'll set that there's a super area in the case right now called Texas. That's just the way that the case was initially set up. We'll take that off of AGC and then allow the AGC to happen across individual areas. So that'll allow us to put transactions between areas, and then they'll actually take effect. If the super area was controlling, then a transaction between areas that were both in the same super area would be ignored. We'll set the area 5, which has the slack bus after it gets moved, to off AGC, and then area 7 we'll put on injection group slack with the coast load as the injection group. By doing that, if we put in a transaction between our new area and area 7, it'll basically be doing the same thing as it will do when we do the PV study later. If I look at my areas right now, let's just take a look at the way the areas are currently set up under aggregations. So we've got 8 areas that were in the case before we added one for La Mesa. And these are all grayed out on AGC status because they're all part of the Texas super area. So if I go here and look at the super area, it's on optimal power flow control. We'll just load an auxiliary file that does all of this. But one of the steps that we're going to take in setting this case up for our analysis is we'll turn Texas off AGC, and I can just do that actually manually right now. And if I do that when I switch over to the areas, then I can see this is not grayed out anymore. But we do want these to be set differently. We want most of them on participation factor, except for the one that will contain the slack bus. We'll take that off AGC. And then the one for coast load, we'll switch that to injection group control, which we can't see right here because we haven't specified an injection group yet. But we'll do that when we load the auxiliary file. So we'll go up here, load auxiliary file, and this is the one, 2040 megawatt control is the one that takes all these steps. And if I just open that up in a text editor, I can see what that does. It's going to be initializing all the buses to not be slack buses, and then it'll set bus 5262 as the new slack bus. It has to do this from edit mode, so we switch to edit mode first. We'll take the super area off of AGC, and then we'll set the AGC settings and also the exports for the other areas. We'll initialize those so that the present case is meeting the ACE equations for all of the areas. Actually, if I look at those right now, when I turn that super area off control, I got all these non-zero ACEs that popped up because the case was dispatched with one giant super area. When I take that off control, then it'll try to enforce these transactions if I went to solve the power flow right now. And I don't want to do that because I don't want to move all of this power around. I don't want that to all be zeroed out. So one of the things that the auxiliary file will do is it will set the unspecified megawatt interchange for all the areas to equal the present interchange so that the ACEs should go to 0. So let's go ahead and load that. The megawatt control auxiliary file. And so, yeah, we see that that's exactly what happened. It populated the unspecified megawatt interchange with the actual interchange, and then the ACEs all go to 0. So I should be able to solve the power flow right now without perturbation from the current system state. The coast area 7, which is where we're going to try to sync the power when we do this interconnection, has been changed to injection group slack control with coast load injection group as the slack. So I'll open my message log right now and just again solve the power flow. It solves without moving from where it was. Now we're going to get into contingency analysis, and we're going to do an initial run on the base case with no output from our new generator, and then we're going to interconnect our new generator and run it again. We will do an auto insertion of single transmission lines or transformers. We'll use area zone filters, and we'll insert elements only at 100 kV and above. So tools ribbon, contingency analysis. I'll do an auto insert, single transmission line and transformers, not all voltages. We'll decheck that so that we can put a minimum of 100, and we'll tie that to the lower end in cases of transformers. And we'll edit the area zone filters to include, so the 3 areas in which we will insert will be Far West, Coast, and La Mesa. Come here and just toggle everything to no except for the ones that we want. And I'll also check the box right here for deleting existing contingency records. There are some that were stored with the PWB or the case file, and I'm just going to wipe those clean and start with a set that only meets these criteria here. So it tells me it's going to insert some contingencies and delete the existing ones, and I'll confirm that that is what I want to do. All right, so on the contingency options, we want to make sure that we're getting makeup power from the entire case. We don't want it to go the case to try to maintain interchange or only get makeup power from within the area that it's needed. And we also don't want to get it from the island slack bus. So we'll make that adjustment on the options. We will also set the limit monitoring to ignore radials and only report violations at 100 kV and above. So here on our contingency analysis, we'll go to options, and it is set to use generator participation factors from the entire case. That's what we want. And we can go from to the tools ribbon and open the limit monitoring, and then go to the area reporting and just use a minimum of 100 kV and up. So we'll set all the values in that column to 100. And we'll also choose globally to ignore all radial lines and buses. Also in our contingency analysis, we'll set up some advanced limit monitoring to always report as violations any decreases in low bus voltages, and also to look at changes in bus dB DQ sensitivity of at least a multiple of 5 from the reference state. And we'll also use this advanced filter right here, which operates on buses with at least 5 megawatts of load and only in areas 1, 7, and 10. So by using a filter there, we can save on processing time because it doesn't have to do a self-sensitivity calculation at every single bus for all the contingencies. On options, limit monitoring, advanced limit monitoring, and we'll choose always report as a violation decreases in low bus voltage of at least 0.05, and then also changes bus dB DQ sensitivity of at least 5, and click the define filter button, and we'll just build our advanced filter on the fly. So one of the conditions for the bus that we want: load megawatts right here. So under the group loads, choose megawatts, and then we'll make it greater than, or let's say greater than or equal to 5. And then we'll add another condition, area number within integer list. Was it 1, 7, and 10? Is that right? Yeah, 1, 7, and 10. So just these two conditions, and we'll make sure that they're ANDed together. And then we'll call it DV DQ check. All right, so now we're ready to run the contingencies, and we have a state right now which is essentially the same as the initial state in the case. We've changed some settings, but we haven't nudged the power flow by actually interconnecting the generation yet. So let me just verify that that's in fact the case. If I go back to my bus view and go back to La Mesa from the history list here, I can see, yeah, again, we've got a current reference state where we're not outputting any power from that generator. So this will be our baseline run for contingencies. And we can do this again with the generator interconnected and compare the results. So I'll go ahead and click Start Run. And we are doing a full AC power flow, but it's a pretty small case at 2,000 buses. Once it's done, we can see we've got some results. Some of these contingencies have branch overloads. Some of them have voltage violations. If I click on this one right here, I can see this isn't a limit violation per se. It's just a change in the low bus voltage. So that would have exceeded our threshold of 0.05 per unit from the reference state. So that's why that's reported. So we just wanted to kind of collect all these base case conditions. Now we can save this out to a file and run the same analysis with the generator interconnected and then compare the two sets. Down here, I'll click the save button. We'll save this to a file because when you do the comparison, you need at least one set to be saved to a file. The other one would be the one that's presently stored in memory. That'll be after we run the analysis on the other ones. So we'll save this out to the file called La Mesa CTG base. Another edition of the file is already in there, but we'll just override it. So we'll click that, and we'll click save. And we want to make sure that we're saving the contingency definitions, and we don't need the limit monitoring settings. This is kind of up to you as far as like how much of this stuff that you want to save. If you want to come back to it later and standardize the same settings on the same case or a similar case that maybe doesn't have all the same settings in them, then you can save those other things. But what we really just need are the definitions, the options, and the results. So I'll just decheck everything else because we don't need it. These options on the right, we'll leave those as they are. And then click OK. And we'll overwrite the existing file. Now I'll go ahead and close contingency analysis because we're going to make some changes to our system, and then we'll want to reopen it and set the new state as the new reference state. So that's easy enough to do if you close it first. So in our comparison case, we're going to interconnect the generator, and it's assigned to its own area, which is number 10, and we will activate that transaction. We can use our bus view one line to just click on these breaker objects right here in order to put that generator in. And what we should notice is if we simply interconnect it and do nothing else and solve the power flow, it should continue to sit at 0 megawatts. It might be producing some reactive power because it's helping to regulate this bus right here, but it's still at 0 megawatts. Then we'll go back to our Model Explorer and we'll right click on Area La Mesa and show its dialog. Here's our list of transactions from La Mesa, and we have one that's not enabled, and we'll want to just go ahead and enable that transaction. That's one that we read in from the auxiliary file earlier, and that'll direct it to export 200 megawatts to area coast, which when we solve the power flow should respond by increasing the load in that injection group that's made up of the load. We can use our difference case tool too to just see like what the difference flows are. I might do that. So I'll go to the tools ribbon, or I actually have it on the quick access right here, but you might not have it on your quick access. So you would find it under the tools ribbon, and then you can go to the difference case, set the present case as a base. Now when we solve the power flow, we should see this area increase its generation, and we should also see area coast increase its load. And now that it's solved, we do have generation there. If we want to look at the difference mode here, we can see that that's what happened. And there's a little bit of generation that went to the slack area as well. some changes and losses that occurred in different areas necessitated changes in their generation as well. So these are all on control, except for the one that contains the slack. So we'll go back to the present mode. Yeah, this is exactly what we did. If we go back and look at our one-line diagram, or our bus view one line for La Mesa wind, we should see, back to that, you can see the 200 going out there. And certainly we can look at difference flows here as well. We can see where that power left on those tie lines and so forth. Switch back to present mode. And then if you left your contingency analysis dialog open, you could go to the other tab and just make sure you set the current case as the reference. I closed it, so it should prompt me when I reopen it. If I go to Tools, Contingency Analysis, it will ask, do we want to use the existing reference case, which would take it back to what it was before with this generator out of service and no transaction, or do we want to set it to the current case, which is with the generator in? That's what I want to do, so I'll click OK on that. And then I can rerun. I'll click Start Run. And then this will give us a set that we can compare to the original run. All right, so once that's done, we can optionally save these results out to a file also if we just wanted them for future reference. We don't really need to do that for our example right now. We'll just leave them stored in RAM, but the slides explain what you could do. You just repeat that process of saving the contingency to a file with the results and with the other options as you like. And then we'll go to the comparison tool. So that's under the other tab. We'll click that, and there's an option right in here that says compare two lists of contingency results. It just kind of explains the terminology here. We call one list the controlling list, and normally you would make that the condition after the change. So that'll be the condition with our generator in the system, and that's the list that's presently open in the contingency analysis dialog and the results that are presently stored in RAM. So then it asks, where do we get the comparison list? And we'll bring that up from a file, which is the default right here. So I'll click Browse and then go in here and choose the La Mesa contingency base. If you wanted to, you could just pull both lists out of a file because we have a stored La Mesa CTG transfer.aux file. You could grab that one for the top list if you wanted to, and then the base for the bottom list. Once I have those specified, I can just click OK. And then it'll ask me in this confirmation dialog, would you like to set the display or the dialog with default columns for comparing contingency lists. And normally you want to do that because you could do this manually and you could add only the columns that you really want to see. But this is kind of helpful, at least as a starting point. You can always edit that later if you want. But what it's going to do is it's just going to modify your display column options to put in some additional fields that let you do the comparisons. And we'll talk about what those mean and what you can get from that next. So here's the list, and if we sort in descending order on the worst branch violation, then we can kind of identify the contingencies that have new problems in them with the generator interconnected, at least new thermal problems. We can also look at worst low voltage situations or worst high voltage situations or worst interfaces or DVDQ, that sort of thing. And we'll take a look at a few of those other ones as they pertain to the actual data we have here. But if I look at just the worst violation, then we can just see in summary, we have two violations. The violations that are numbered here and then also in the max branch percentage deal with the last one that we ran, or the one that was in RAM. That would be the situation with the generator interconnected. The comparison violations are the ones that occurred in the base case, so with no generator interconnected. So this tells us we have two overloads now that occur on this contingency right here, which is the outage of La Mesa to Stanton. This is actually one of the lines that comes out of the transmission level from La Mesa. So if we take this line out of service, we're probably going to get some overloads here. And those are new violations that did not occur when this generator wasn't producing any power, which kind of makes sense. If when we interconnect that generator, now we've got new flows on these transmission lines and new violations that occur. So we might conclude that interconnecting the generator would require us to either upgrade the transmission that comes out of La Mesa or have some sort of remedial action in place that would curtail La Mesa if there's any loss of transmission in the area. The meaning of the worst branch violation really depends on whether there were any overloads in the comparison case or the base case or not. But the max branch percentage, that's just the worst overload in the current case. So the last one that we ran, which would be with the generator interconnected. The comparison max branch percentage is the highest overload in the original case or the base case with no generator interconnected. And then the worst one, again, really depends on whether there's an overload in both of them or only in one. If the overload is present in both the controlling and the comparison list, then the highest is just the difference between the two numbers. There can be some violations that occur in both. And if that's the case, then the difference is just the difference between the two. If there are violations that occur only in the new case, but they didn't occur at all, there was no overload before, then for purposes of determining which one is the worst, it's just the worst violation minus 100, because we don't know what the loading was in the base case because it wasn't a violation and it wasn't flagged. We end up with a percentage of 163 is the worst percentage overload in the new case for this contingency, and that subtracted from 100 gives us 63.8. So if we scroll down here, we can see the total list of contingencies. There's only 72 that give us new violations that were worse than what we had before. And there's some down here actually at the bottom of this sort order where putting the generator in actually alleviated some of the overloads. So it was worse in the comparison case than it is in this case. So that's good. And then for the vast majority of the contingencies, they were either no violations or no new violations. So these are the ones that we could focus on. And we can also browse these results by element too. If we go to our results tab and we look at viewing the results by element, we can look at branches, for example, and look at the worst increase violation and see which elements are impacted by higher loadings in the case with the generator interconnected versus the base case. Here's an example where we have a couple of overloads that were not present in the base case. So it's just the new case or the controlling case values minus 100% to get the worst. We look at it by element and we get similar values reported by element and similar methodology for determining the worst percentage. So if we look at this element Houston to Houston, that's a transformer. It has 4 violations that are in the present case. None of them are new, so they occurred in both. And we have cases where for some contingencies it went up by 1.6%, some of them by 1.1%, and then the worst is just the highest of all of those values. So we can see that here. There was 4 different contingencies that caused overloads, and they caused overloads in both cases. But it got slightly worse for the case with the generator. So next we'll look at power transfer distribution factors with respect to the injection of power at the new unit. And we'll first just go back to our base case by disabling the transfer that we added between area, La Mesa, and coast, and then we'll go into the PTDF dialog and do a transfer. So for now, I'll close contingency analysis, and then I'll go to the Model Explorer, and then under Areas, just go back to that dialog and disable that transaction, and then solve the power flow. So now we've got no export. We're kind of back to our base case. We might also just want to have a version of the base case that we could reopen. For purposes of going through this exercise, we can just take it back to the starting point this way. And then we'll go to now the tools and then the sensitivities and look at PTDF. So we can calculate this between area, La Mesa, or we could also use alternately the injection group La Mesa. Should do the same thing. And then go to the injection group coast load and calculate those. And of course we can browse them like this, but we might also want to put them on the one-line diagram. We could do that either with a contour, or we could do it with flow arrows, or both. We just come over here back to our one-line diagram. And I'll zoom back out. I think we have a saved view. Yeah, we have a saved view that just looks at all of Texas. Resize this in order to get everything in there. We'll go to our one lines. We'll go to contouring. And we can just apply these. These defaults are here saved. with the one line diagram. So we're going to contour line and transformer PTDFs just from 5% and above. So by ignoring zero values and ignoring below minimum, it should make the calculation a little bit faster to put them on there. I can hit recalculate. If I want to play with any of the other parameters, I can do that. And that just gives us a good look of where the power is flowing from here out throughout the network and coming into this region down here. If I wanted to clarify this a little bit too, I could take things like the arrows off, the animated flow arrows. I could just turn those off. Makes it look a little better. We might also adjust our one line options so that we don't show all the substation dots or take the pie charts off, things like that. It gives a good feel for how the power is traveling through the network, and that's a nice visualization which can be put in reports or presentations. We could also show the PTDF as the flow arrows, the animated flow arrows. We can just switch that to PTDF, and we might change the pie charts as well. Yeah, I can just apply that and then adjust the limits accordingly. Might make the size a little bit bigger. Add another 0 in there. Take the contouring off. You can see it that way too. And then we might want to just take that to the next step, and instead of just knowing where the power flows, we might want to know when the limits are actually hit. And of course, we can do that with the available transfer capability tool. I'll close the PDF dialog. So now we'll go to the add-ons ribbon, then open the ATC. It just grabs the same parameters for seller and buyer as what you last used in the PTDF tool. We'll look at a maximum transfer limiters of 25 and also 5 per contingency, 5 per element, and ignore anything that's less than 3% PTDF. And we'll iterate on a single transfer limiter. And to do that back here, just change this to 25, 5, 3% for OTDF and PTDF. We'll do the iterating on a single transfer limiter, and then go ahead and run the results. And it happens pretty quickly because we're, again, using linear methods and we're only iterating on the worst case one. But then this shows us that we're most limited by this contingency right here that opens O'Donnell to Snyder, 230 kV, and then we get an overload on the 115 kV network with a transfer level of just 100. So we can also look at this and say, these are all the issues that maybe need to be addressed in order to be able to get up to a 200 transfer level. So we have elements and contingencies that tend to kind of recur too. So if you can kind of fix the worst case for some of these elements, then you would expect it to be better for the other ones as well. And just also note that there's a set of auxiliary files that go through the ATC process as well. I won't bother running it, but we can look and see what's in there. Just kind of gives you some ideas if you want to be able to replicate a similar process and do it on multiple cases. Maybe you've got a spring case and a summer case, and a light load case, and you want to just run the same type of analysis on each of those and do it the same way each time. One way you could do that is through scripting or auxiliary files. So if I open this one, I can see that if you start with a base case, it'll load a file that'll actually do the interconnection, load contingencies, load ATC settings, and then run and save the results. So the one that runs and saves the results is right here. So it switches us over into ATC mode, closes the transformer, the step-up transformer, and the generator, solves the power flow, runs the ATC between the seller and the buyer injection groups, and then saves the results to another file. And then, of course, we could just look at that file, or we could load it in after we run it. And it would have got the contingency records that were used. And at the very bottom, it's got the results themselves. So the same results that we're just looking at in the user interface. Then we also have this PDF document where you go to the Window tab, you open auxiliary file format, search the document for that. Maybe need to start a little bit higher. ATC related actions are in this section of the document right here. So the ATC determine command, which is in that script file, is here. So you identify the seller, the buyer, and there's an optional flag on whether or not to use distributed computing. So there's the seller can have all these different object types. So the format of this argument, is either an area with an area number, area with an area name, or area with area label. Those are basically the three different alternate key fields for that object type. Super areas will either have name or label. Injection groups will have name or label. Next, we'll do some different types of voltage analysis. One type of analysis we might want to do is plot a QV curve at the point of interconnection and just see if dropping the new unit on the network has a positive or negative effect on reactive power margin. We would want it to be, either positive or neutral. So for PV analysis, if you have a huge list of contingencies, it can be rather time consuming to run through that. It's not like ATC where we can use linear methods to identify the most limiting contingencies and elements on the transfer. The technique that we'll use just here is we'll run out the PV analysis on the base case to see where it collapses, and then we'll back off the transfer a little bit from that point so that it's still stable, but only marginally stable, such that if we run a bunch of contingencies, we might expect the most severe ones to not solve. And then that'll give us contingencies that could be the most limiting to the transfer. And then we can rerun the analysis with just that short list of contingencies so that it would take a lot less time. And then optionally, you can run some QB curves on load buses or other kind of weak points during the transfer to identify what could maybe be done to support voltage if the PV analysis ends up being limiting. What we'll find out from running this is that it's not very limiting. We can ramp out our generator well beyond its planned capacity without any issues. So the rest of the stuff is just kind of optional. So to look at QV curves at the interconnection point, we might, kind of like what we did with the contingency analysis, we might want to examine a before and after. So run it without the proposed generator and then run it again with the proposed generator. And we might say that if the reactive margin decreases, then we might need some supplemental reactive support in that region. So we'll just take a look at the base case without contingencies, and we'll also set our options in the QV to disable switch shunts, SVTCs, LTCs, and phase shifters so that we look at what's happening in a steady state or a short-term time horizon. And then we'll also want to set our minimum per unit voltage for constant power loads to be 0 so that the loads can be fully stressed and that they won't be curtailed as the terminal voltage drops. For constant power loads, that you would expect them to be constant even as the terminal voltage changes. So we can load these options from, actually this is an old auxiliary file, but let's go to the case here, and then so we've got the unit not operating right now, but I think it is still connected to the network because of what we were doing with the ATC. So I'll go back to this bus view and I'll disconnect the step-up transformer and the generator itself, and then solve the power flow. So now what I want to do is go to the add-ons, and we'll open the QV tool, and we'll scroll down to bus 1089. You can also search for it, but it's not too far down the list. And we'll toggle its QV selected to yes. We won't quite track any additional quantities. We'll just plot the QV curve. And these options will just kind of leave the same. And then what we might want to do is open the QV power flow solution options and then make sure that these other controls are locked. We might use SVCs. I don't think there are any in the case though, so I don't think it matters, but those tend to be faster devices or could be faster devices. So maybe we want to allow those, but for our purposes, we'll just do all of this, and then we'll set the minimum per unit voltage for constant power load to 0, and then also for constant current load to 0. And then our contingencies tab will just run the base case. So I'll clear this checkbox right here. And we don't need to save the results to the file. We'll just plot them. And we'll plot, we can plot as computed. That's fine. We're only going to plot one since we're skipping the contingencies. If you have a whole bunch of contingencies and you want to plot some of them, then you might not want to check that box. Otherwise, your screen will fill up with windows. Go ahead and run the analysis. And it's tracing out different voltage set points. So, of course, we could save that out to a file, a JPEG, or something like that. Copy it to the clipboard. Okay, and then with the proposed unit, we might just repeat this exercise with the unit in service. So go back to my one line diagram. Put the unit back in service, solve the power flow, go to my transaction. I could go back to the area diagram or the area dialog like we did before. Oops, actually that's not under aggregations. We can also just look at list of transactions too. And we simply have the one that we added. Just enable that. Then go back to the bus view online and just make sure that it solves and we get a dispatch. Then we can come back to our QV curves and just run that again. Now we get a Q margin 79, or we can read it off 76.62. It's a little bit of a decrease from the base case. We could conclude that we need additional reactive power supply, but we could also conclude perhaps that it provides a safe enough margin to operate the unit itself. You got 161 without the unit there and 77 with the unit there. All right, so next we'll do a PV analysis, and I'm again gonna take us back to the base case. I'll leave the unit interconnected, but I want it back down to 0 again. And again, we can quickly do that just by not enabling the transaction there. And then again, solving the power flow. Or as mentioned before, we could have just a version of the case that is saved in this state and then just reopen it. Which, if you're going back and forth a lot, that might be a better quality assurance procedure. Make sure that you're always starting from the same point and you didn't inadvertently tweak something that you didn't mean to. With the PV study, we'll just look at the ability to transfer power from the proposed generator to loads in Area 7. It's the same transfer that we've looked at with the ATC when we just interconnected the unit itself for purposes of running contingency analysis or for running the QV at the point of interconnection. We're going to use a screening process so that we don't have to wait for the PV to run for all of the contingencies, because we have almost 1,000 of them and that would take a very long time. So we'll start by just running the PV out on the base case only. And then we can repeat that run, but we'll stop the transfer when it gets to about 80% of the level that's determined in the base case PV run. From that point, we'll launch the contingency analysis and then run those and then identify those that failed to solve. Those contingencies then will be the ones that we'll use with the PV, and it should be a shorter list. If it's not, you could play with these parameters too. If you end up getting too many contingencies that fail or none that fail, then perhaps you can adjust the parameters, or if nothing fails, you could still maybe identify the ones with really low voltages or high changes in DVDQ multiples or whatever. But these are the parameters that we'll use to initially check it. So the PV setup, we'll use, again, our injection groups that we've been using for other transfers. We'll stop after one critical scenario. Since we're not running any contingencies, then the only real scenario is the base case. So there's nothing else to do after that. We'll use a 200 megawatt initial step size with a 10 megawatt minimum. So coming back over here, we'll go to add-ons, PV, and choose as our source La Mesa and as our sink the coast load. One critical scenario, skip the contingencies. On the options for the ramping, we'll use the injection group source sink method to ramp, and then we'll also not enforce megawatt limits. So that will let the unit continue to ramp beyond 200, which we'll need to do. As we've seen before, we can easily transfer 200 and solve all of our contingencies without any issues. So we've got a good idea that the nose point is somewhere beyond there. If we want to go all the way out, we need to not force megawatt limits. Check that. We don't need to worry about negative loads because the loads are only in our sink area and they're going to grow more positive or larger. On the advanced options tab, we'll have it maintain the megawatt megavar ratio at each load and then scale the megavar by a unity factor, which means don't scale it. So that'll essentially move the megavars up in the same proportion as the megawatts. Yeah, now we can run it. So we'll go to the PV results right here and just run. Oh, I have an output file in here. That's okay. Just say yes. I guess that must be stored on the PV output tab right here. We have a file. That's what that was in reference to. Okay, so it runs out to 337. That's actually not too far beyond our 200 megawatt limit. You know, we've got a base case limit of 337. If we wanted to plot this, let's see, we didn't track any quantities, I don't think. So there's nothing to plot right now. Is that right? Oh yeah, no, we can plot. We can plot at La Mesa. But that's probably not going to be very interesting. So let's just carry on with our plan here. So yeah, we want to go back to the initial state. If we browsed our system state right now, we would see that we have 337 coming out of La Mesa. We're at our critical point right now, and we want to back that off. So we'll go back to our initial state and then restart it out to almost that point. So here under other actions, we can go back to restoring the initial state. And now to jump out to like an 80% level, we'll run the transaction out to 275 megawatts. And if this was a far enough point that we couldn't set it right away without having some issues, we could use the PV curve tool to just stop at 257. So if we come up here, we could just say stop when the transfer exceeds 257. But it's not very far beyond where we were able to set it before, and we should just be able to do that in one step by just enabling the transaction and ramping it out there. We might first solve it at 200 just to make sure, but we can enable that. Then solve the power flow, make sure it solves okay. And again, look at what's going on at La Mesa. We're at 200. And then just jump this out to 275. So we put a negative 275 in this particular dialog because the export area is actually our receiving area, which is coast, and then the import area is La Mesa. I'll do that. Then see if that solves, make sure that solves. And look at my power flow solution. Yeah, and I've got a power flow solution right now. I'm not sure if we have any stressed voltages just in the base case. We could go to our limit monitoring. We've got overloaded lines. Of course, most of those are really close, but we don't have any, at least low voltage buses in the base case. But if we run the contingency analysis, we could see some issues. So let's do that again. We'll go to, I don't have it open right now, right? Yeah, I don't. Go to Tools, Contingency Analysis, and we want to set the reference state to the current case. So with our 275 megawatt level of output, and then we've got our 968 contingencies are still in here, and we'll do the run right now. All right, so this is done. We've got a whole bunch of violations compared to what it was when we ran it before. But we're not so much interested in that. You know, we've already kind of done the thermal analysis with the ATC. We want to kind of look at voltages right now. And we can see we have 5 contingencies that are unsolvable. So if I sort on violations, then the ones that are unsolved, just say that they're not solved here. Or I can also, you know, sort on the solved column right here. So these are ones that cannot solve with an output of 275 from the unit, and of course with the loads going up 275. Yeah, these are the ones that we're going to want to look at. So to set this up to run the PV analysis with these contingencies, what I'll do is I'll go to the skip column right here and set everything to yes, and then just toggle back to no the ones that are unsolved. Close this. And now I want to get back to, again, my starting point case. So I'll go to my transactions in my Model Explorer. And, you know, maybe I want to back this down kind of gradually. 200 first again. Solve it. Maybe a 100. And then solve it. And then just disable it. And solve it. So here I'm ready to start my PV analysis again. I'll come back here to the PV curves. And now I'm going to not skip the contingencies. We might also want to track some buses that experience low voltage. Yeah, we could look at various values of the transaction between, let's say, 225 and 250, and then solve those contingencies and report as violations decreases in low voltages and changes in bus dV/dQ sensitivity. So this kind of helps us identify where we might want to plot the PV curve right here. So actually, I'll close this and I'll go back to where I was. Let's enable this transaction again. Say, let's go to 5. And we can go to our contingency analysis again with the current case as the reference case. And Again, a lot of these options we had already set up before, but if I go into my advanced limit monitoring, I still have these settings right here for always reporting changes in voltages, and then also DVD key sensitivities. I could see we'll just clear the skip no results, and let's see. Oh, sort this by skip now. Okay, so yeah, we've got some buses that drop in voltage under the contingencies. We've also got some buses that change low voltages. So Stanton and La Mesa are ones that kind of show up here. And yeah, we could look at bus results too, right here. La Mesa, Stanton. So these are ones that we might want to track. We could show some of those fields. O'Donnell and Oklahoma, I guess, are also identified. I won't keep doing this, but you know, if we could ramp the transaction out to 250 and see what happens. But yeah, Stanton and La Mesa are what we just identified at 225. So we'll go ahead and track voltage at these places right here. I'll just go ahead and close this. And we'll take this transaction back down, starting point. And then go back into the PV analysis. And under quantities to track, 1022, 1028. 1054 and 1089. Okay, we're already doing 1089. And we might want to look at megawatt output and megawatt reserve at La Mesa Wind. So that would be for either generators or injection groups. We could do either one of those. Megawatt reserve. We initially ran out with a step size of 200, and we hit a limit after just taking a couple of steps. We know we're going to hit our critical scenarios on that order of 200 to 250 to 300, kind of in there. We'll do an initial step size of 25 megawatts and a minimum of 5. A little bit higher resolution where the nose of the curve is. So on setup, do initial step size 25, minimum of 5. And again, we'll stop after 5 critical scenarios, and we won't skip contingencies. And we can optionally just run our base case to completion, which would be an additional scenario on top of this. And sometimes that's useful if you want to plot the contingencies on the same graph as the base case. And if we want to do this integrated QV analysis, there's an option on the QV setup to do that. You can say, let's automatically launch the QV analysis at the end, and then we need to pick the correct options file, and that's called La Mesa Integrated QV Options. And what this file has is just a set of options for solving the QV, and then also some quantities to track. So like our La Mesa bus and some generator quantities like megavar reserves and so on. So we'll point to that. Coming to our PV results, click run, and yeah, we'll just overwrite that file. We see that we reached the nose on all these contingencies, you know, in the 225 to 262 range. And then here's our base case, which it ran out. So we have the 5 critical scenarios plus the base case, which is critical too because it ran to completion. Yeah, and if we wanted to put all of these on a plot, this is looking at the Stanton 1054 bus voltage against all the contingencies, with the base case being the longest one. Do that by going legacy plots right here and just saying let's plot everything. And then for our horizontal axis, we can put the output of La Mesa wind, and then we can put per unit voltage on the vertical axis, pick Stanton, and plot it. Or if we wanted to see one of the other buses, like the La Mesa interconnection point, we could do that too. Yeah, that's rather abrupt. I think what's happening is it, you know, runs out of reactive power support and then starts to drop off at that point. Yeah, in summary, we might conclude from all this analysis that we do have some thermal violations, particularly around La Mesa, that are caused by the interconnection. And certainly as we go beyond 200, we run into some voltage issues, and we might need some transmission upgrades in order to support the interconnection. Yeah, when we finish, if we want to run integrated QV analysis, we could tell it to launch the QV curve tool. Again, it's leaving us in this state of with a 337 megawatt output. So we can do a QV analysis at that point. Oh yeah, it starts running automatically. So it launches the QV curves and then it runs it. And it's running it for all of my contingencies too. And we can see for the base case, we've got a Q margin that's very close to 0, which is because we're kind of at that critical point for the base case. So we could plot that one. You know, it pretty much rests right on the intercept of the axis. But then on these other ones where we have like these high Q margins, this contingency right here, we can see it actually sits up above the axis. So there's no solution without adding supplemental reactive power. So we could, if we just wanted to dive into this issue a little bit deeper, we might say, well, what if we put some reactive power support of at least another, you know, say 120 to 200 megavars at that point of interconnection? Would that allow us to be stable at higher transfer levels? But you also might conclude that the thermal issues are much more limiting. So resolving those might beef up the system enough that the voltages look better. I won't go into all the details on this. These slides are just kind of provided for information only, but you could run the QV analysis at 200, add a switch shunt of 120 megavars capacity at the interconnection, and then repeat that and see if that improves the margin. In fact, it does, although the voltage falls off pretty sharply right here. And then we could also rerun the PV analysis with the capacitor inserted there, and we might find that we're able to get higher margins on the PV transfer as well. We have a most limiting case of 386, which is better than what we saw before. This is just showing voltages fall off. We tend to get negative dB/dQ sensitivities near the PV margin. Stuff kind of bouncing back up the other way. That's an unstable solution, and then it eventually collapses. 400 megawatt transfer. If we calculate the self-sensitivities at that level with this particular contingency taken, then we get negative dB/dQs at La Mesa and Stanton. So that's why you get this uptick in the curve here.
If you need further assistance, please feel free to look us up on the web, give us a call, send email to our support line, or if you prefer to work with a particular Power World engineer, please feel free to contact that person directly.